Hi students, in this video you will be learning a very important question from intermediate second year physics. This question is very important. The question is, explain the formation of stationary waves in stretched string, deduce the loss of transverse vibrations in stretched string. Let us understand the first part of the question, that is formation of stationary waves in stretched string. Let us consider AB is a string which is fixed between 2 points. When you pluck one end and release it, when you pull the string and release it, waves start from here and it will move to the other end. When it touches the other end, it reflects back. It reflects back and travels in opposite direction. Thus, in this case, there are two waves. One wave is moving forward and another wave of the reflection moving backward. Thus, two waves are traveling in opposite direction. When two waves of same frequency, same amplitude, travels in opposite direction, and if they overlap each other, then stationary waves will form. In stationary waves, there are certain points. These points are called as nodes. Here, the amplitude of the waves will be 0. And there are certain other points. These, they are called as antinodes. We can represent with AN. These points are called antinodes. Here the amplitude will be maximum. So in this way, stationary waves will be formed. Let us see the next part of the question. Here we have to deduce the loss of transverse vibrations in stretched string. For this you have to know this diagram and these basics. So in the basic you can see distance between two nodes lambda by 2, speed of sound v is equal to n lambda, velocity of transverse wave in stretched string v is equal to under root t by n. Here in the diagram you can see the total length of the string L is vibrating into many loops. Here one loop, here two loops, here three loops, and so on. So we will consider as P loops. Therefore, length of the string and how many loops are there? P loops. So initially how many loops are there? We will take that example. So initially one loop is there and here we have two nodes. Therefore, distance between two nodes is how much here? Lambda by 2. So distance between two nodes is equal to how much initially? L by P. P means what? Number of loops. So from here we can get lambda equal to, these two will go there, 2L by P. Make this as equation number 1. Now use speed of sound formula, that is, we know that V is equal to N lambda, equation 2. Substitute the value of 1 in 2. In 1 you have the value of lambda, we will write in here. So V equal to N, in place of lambda 2L by P. Make this as equation number 3rd. Now we have to use velocity of transverse wave in string formula, V is equal to under root T by M. We will write here, we know that V equal to under root T by M, equation 4. Now you can see here in equation 3 and equation 4 on LHS V are there. That means we can equate these two equations. Therefore, equation 3 is equal to equation 4. So what is equation 3? N2L by P. N2L by P equal to under root T by M. So what we have to find here? The formula of N we have to find here. Therefore, from here we can write N is equal to, this P will go here. So P by this 2L will come here, 2L under root T by M as it is. So this is the general formula of frequency in case of stretched string. From this only we will deduce the loss of transverse vibrations. Now let us write the three laws of transverse vibrations in stretched string. First law. If you remember this formula, then first law, second law, third law easily we can write. The formula is n is equal to p by 12 under root t by m. Here in place of p we will write 1. So the formula is n is equal to 1 by 12 under root t by m. First law. When you are discussing first law, we have to discuss n and L, where n is frequency, L is length. So frequency of vibrating string is inversely proportional to length. Why we are telling inversely proportional? Because this is in the denominator. That's why when we compare these two, so it will become inversely proportional with n. Therefore, first I stated frequency of vibrating string is inversely proportional to length. So here we are not discussing about tension and linear density. Therefore, we can tell that tension and linear density are constant. So this is first law, simple. Frequency of vibrating string is inversely proportional to length, where tension and linear density are constant. We can also write the same equation as n L equal to constant. Let us see the second law. When we are discussing second law, here we have to discuss about frequency and tension. We are not discussing length and linear density. Therefore, we can write frequency of vibrating string is directly proportional to square root of tension. Square root of tension, and here we are not discussing L and M. So we can write here L, M are constant. So this is second law. Frequency of vibrating string is directly proportional to square root of tension. We can write this as n by under root t is equal to constant. Let us see the third law. Third law, we have to relate frequency and linear density. It is inversely proportional. Why? Because it is in the denominator. Therefore, we can write here frequency is inversely proportional to square root of linear density. Inversely proportional to square root of linear density. Here we are not discussing length and tension. That means L and T are constant here. This equation we can write n under root m equal to constant. So these are the three laws which we have deduced by using this equation. Let us see the last part of the question. We have to derive the equations of frequencies in different modes. For this, we have to know the basic formula of frequency, that is n equal to p by 2L under root t by m. If you remember this formula, then easily we can derive the equations for different modes, that is fundamental frequency, first overtone, second overtone. When the loop is 1, that means when the string is vibrating in one loop, we call it as a fundamental frequency. When the string vibrates with 2 loops, then that is called as a first overtone. If it vibrates with 3 loops, then it is called as a second overtone. Now we have to derive the equations for each of them one by one. Let us see the first part, that is for fundamental frequency. In case of fundamental frequency, how many number of loops are forming? 1. So here only one loop is there. So P means number of loops. So P is equal to 1. For fundamental frequency, we represent with letter N naught. Fundamental frequency is also called as first harmonic. First harmonic. You have P equal to 1, N equal to N0. This is, for example, equation number 1, and this is equation number A, for example. So put 1 in A. So if you write P equal to 1, N equal to N naught in equation A, you will get the equation of frequency in case of fundamental frequency. Therefore, in place of N, N0, in place of P1, and these two L as it is, under root T by M as it is. That's it. We got the equation of fundamental frequency N naught equal to 1 by 12 under root T by M. Now for first overtone. First overtone. First overtone is also called as second harmonic. Second harmonic. So in second harmonic, 2 loops are there. So number of loops are 2. Therefore, P equal to 2 we can write. And For frequency representation, we will represent N1. Make this as equation number 2. If we put equation number 2 in equation A, we will get the formula of first overtone. Therefore, in place of N, N1 we will write. In place of P, I can write 2, and the remaining terms as it is. So N1 equal to 2 by 12 under root T by M. Here, this value we will replace with letter N0, because N0 is equal to 1 by 12 under root T by M. Therefore, N1 equal to 2 N0. So this is the second case, that is second harmonic. Now let us see the last part, second overtone. Second overtone is also known as third harmonic. So in this case, number of loops are how many? 3. 1, 2, 3. 3 loops are there. So P equal to 3. For this, we can represent with letter N2. Make this as equation number 3. Put 3 in equation A. So in place of N, we can write N2. In place of P, we can write 3. This 2L as it is. And this T by M as it is. Here also we can replace 1 by 2L under root T by M with N0. So we can write N2 equal to 3N0. Thus, this is the equation for second overtone, frequency in case of second overtone or third harmonic. Now let us compare the frequencies. So first fundamental frequency, first overtone, second overtone. Fundamental frequency N0, first overtone N1, second overtone N2. So N0, let us take N0 only. N1 we can write 2N0. N2 we can write 3N0. So here N0, N0, N0 is common. So we can write 1 is to 2 is to 3. So from this we can show that the frequencies in case of stretched string is vibrating in the ratio of 1 is to 2 is to 3.